So, welcome everybody this morning to another UCAR Africa Initiative Seminar. My name is Ana del Moral. I think that I already introduced myself in another seminar. I'm part of the UCAR Africa Initiative workshop working group, and I'm a postdoc at the Earth Observing Laboratory here in NCAR. Today I'll be hosting this session. Today we have our speaker, Justin Small, project scientist at the Climate and Global Dynamics Laboratory, who is today going to talk about coastal upwelling of Southwest and Northwest Africa, and how well is it represented in global and regional climate models. Justin received his PhD in oceanography at the National Oceanography Center in the United Kingdom. And after his PhD, he worked at the Winfrith Technology Center in the UK, the International Pacific Research Center in Hawaii, and the Naval Research Laboratory in Mississippi. And he finally joined NSF NCAR in 2010. So Justin's research interests include air-sea interaction and the effect on boundary layers, oceanic boundary currents, and coastal upwelling. And he uses tools such as the high-resolution CESM and regional system together with satellite observations. He was involved in the first century-long simulation of this same model with a 1/4-degree atmosphere land and a 1/10 of degree ocean ice. So I know that he will talk more about the details of this last sentence that I said in this talk, and we're looking forward to it. So Justin, thank you so much for being our speaker today in this seminar. You'll have 45 minutes, 50 minutes for this talk, so to allow the audience to get the questions going. For those online, we have the Slido system, so you put the questions there, and we'll solve those questions at the end. And for those in the audience, we'll wait for the Q&A. So thank you so much, and the floor is yours.
Well, thank you, Anna, and thank you for the opportunity to talk to the UCAR Africa Initiative. So initially, when I heard about calls for talks for this initiative, I was thinking, I don't work that closely on Africa. But then I realized, well, I'm an oceanographer, and I do look at the boundary currents around Africa. So I'll be talking about the Benguela current, the upwelling, which affects countries such as Angola and Namibia, and also Canary Current, Northwest Africa upwelling affects from Morocco, Mauritania, Senegal. So quite a large region of the western part of Africa is affected by what I'm going to talk about today. A number of collaborators I've worked with over the years since I joined NCAR, and actually my first project, the PIs were Enrique Kachitsa from Rutgers and Bill Large from NSF NCAR. More recently, I've been working with Texas A&M, and I'll call out names later in the talk, as well as my oceanography and CGD colleagues that are also listed there, provided major support and got a lot of these simulations run that I'll be talking about. So as an introduction, this is a map of the chlorophyll from satellite over most of the globe, pinpointing areas of high productivity in the ocean. And the 4 boxed regions shown here they're commonly referred to as Eastern Boundary Upwelling Systems, or EBUs. And you can see that they're regions of high productivity and high chlorophyll. And this paper from a review paper by Chavez and Messi in 2009. And these EBUs only occupy a very small fraction of the ocean surface, I think maybe about 1%. This is a famous quote I'm listing here. But they produce about 20% of the global fish catch, worth up to about 400 billion currently. So these are important regions for a global food supply. And just focus from the same review paper, look in a bit more detail at these systems, and I've boxed the African systems, but I'm going to be comparing with the Peru upwelling and the California current system, which are the two other main ones. And I'll point now that I think the colors are the chlorophyll. The bars here, and particularly the red bar, let's go up to the key here. The red bar is the fish catch, estimated, times 100 grams carbon per meter squared per year. And what you see is that of Northwest Africa and Benguela, these are the amounts of fish catch. Of Peru, it's got the highest amount of fish catch. So that's kind of much more than other regions. And I'm not a biogeochemist or biologist, so I'm not going to try and explain why. But I'll just point out that the Northwest Africa and Benguela are a bit more comparable to the California system, which, as most people know, is a big fishing industry in the United States. So important regions to get right in simulating. So an overview of my talk, I'll start with a bit more introduction about upwelling, why and where it occurs. Then I'll move on to global coupled climate model representation. And I'll just point out, I'll be focusing on the community Earth system model, which is heavily used in CGD and in the university community and elsewhere. Then I'm going to move on to regional climate models. That I just want to make another point about the global climate models, that CSM has many similar aspects to the kind of multi-model representations that have been shown in CMIP5, CMIP6, and also the high-res models in high-res MIP. Regional climate models can show some WRF and ROMS results. Then I'm going to talk about historical upwelling, where we force an ocean model with known atmosphere state and see how the variability is represented, and also talk about a biogeochemistry and fish model, and finish with, is upwelling going to change under climate change? This is a big question that many people are looking into. So I'll start with the introduction, a bit more about, very schematically, the dynamics of upwelling. This is from a paper by Rikachewski and Checkley in 2008. And it's showing an eastern boundary here as a sloping boundary. And these black vectors on the top here are the wind vectors. They're flowing along shore. This is appropriate for the northern hemisphere as it happens, so they're flowing southwards, such as California current system. And another thing I'll point out, the size of these arrows is linked to their strength. So it weakens as you go along shore. But firstly, when you have this alongshore winds, you have what's called an Ekman flow away from the coast. The integrated ocean flow in the upper layer will be away from the coast due to the effects of Earth rotation. And so that forms a divergence at the coast, and the water is replaced from below. That's the red arrow. So this is the classic Ekman upwelling. And in this schematic, you see that the ecosystem likes the cold and high nutrient waters that are upwelled. The second thing that was pointed out in this paper was that, as I say, the winds strengthen as you go offshore. So that is a horizontal shear in the winds, equivalently a curl, a wind stress curl. And the other process is that you get vertical motion due to the curl of the wind stress. That's represented in this schematic by these yellow arrows. So this is further offshore, and it may be causing different communities. I'm not an expert on this, but that's what the paper was proposing. So you have two different processes in this schematic, the classic coastal upwelling, this red arrow, and then this further offshore, what they call Ekman pumping or wind stress curl upwelling. And people have proposed various indices and measures of the transport. So this first one is this coastal upwelling, which I just talked about, classic Ekman transport, and the index was introduced by Bacon in 1973, famous paper in oceanography community. And this is the integrated offshore flow, this U Ekman here. And it's the alongshore wind stress is marked tau A here, divided by density times Coriolis. And I'll often in this talk approximate alongshore with just meridional, because many of the boundaries are approximately aligned with the meridional. I'll call that tau Y. So that's a terminology thing for later in the talk. So that's the classic index. And then since then, people have looked more processes. So the wind stress curl, which I just talked about in the previous slide, and also geostrophic current effects introduced in these papers. This is the curl of the wind stress, which is called the Ekman pumping, divided by density times Coriolis. So this is another important factor. This is the vertical motion near the top in the upper ocean layer. And then another factor is geostrophic transport, and this was not really recognized early on, and including by myself. I thought more typically in terms of these wind stress measures. These top two are dependent on the wind stress. This bottom one is not directly dependent on the wind stress. It's a geostrophic current. It's dependent on gradients of the sea surface height. That's this delta SSH over a distance here. And then this is integrated over an upper ocean layer of width d. So, and I was initially a bit confused by the fact you could have this, because if you go in the interior ocean or atmosphere and you just have a purely geostrophic flow, it's approximately non-divergent. But if you go to the coast, because you have a coastline and a singularity of the coast, you can get this effect. That geostrophic flow can be important. And it doesn't have to be particularly strong. This Ekman offshore transport is not a very strong flow offshore, it's a few centimeters a second probably. So the geostrophic transport does not have to be very strong either to be comparable to the Ekman or wind stress part. So these are some measures that have been used, and I'll come back to them. Looking at a global map of where the upwelling favorable winds are, this map is showing meridional wind stress. Actually, it's meridional wind in this case, meters a second. It's from one calendar month, April, but it's kind of representative. And what you see in the northern hemisphere are the southward winds along the coast of California and of Northwest Africa. And then in the southern hemisphere, you have northward winds off Chile and Peru and off Southwest Africa. These are the sign of the winds that are favorable to this Ekman upwelling. And yeah, as a part of a broader context, maybe if you look at this lower map, these winds occur on the eastern side of the subtropical gyres. For example, down here, the subtropical anticyclone of the South Atlantic here, and the winds along the coast. A little bit hard to see in this, but I just wanted to show the context. And similar for Northwest Africa, it's on the edge of the subtropical gyre where you have the trade winds blowing strongly along the coast. And another piece of kind of atmospheric context is that these regions tend to be regions of low stratocumulus cloud. This is the low-level cloud percentage from a data set, Warren et al. And here off the Benguela down here, you see there's a local maximum of low cloud. A bit less so off Northwest Africa, but definitely off Peru and Chile and off California. It's kind of well known. You have this low cloud even in summer. And there's an interaction. You get the cold water from the upwelling. That can actually help support the stratocumulus clouds by providing a stable environment in the atmosphere. But I won't talk much more about the clouds, but I'll just acknowledge that they're another important feature. And just now start focusing back on Africa. This is just a zoom in of previous plots. This is the region of Northwest Africa I'm interested in, from Senegal up to Morocco. In the summer, it extends up to the Iberian Peninsula, Portugal and Spain. But further south, you get the upwelling more year-round. And likewise, in the southern hemisphere of Angola and Namibia, there's a maximum in the winds. And these are where these high productivity and high chlorophyll regions are. This is the Congo outflow, which I'm not going to talk about here. That's the other productive region here. So a little bit more about the Benguela. It's a region of ocean fronts and a double core atmospheric low-level jet. So this schematic on the left here is showing the flow. The black arrows are the Benguela current. There's an offshore branch, and there's also an inshore branch, which is most associated with the upwelling. But there's also an ocean front between cold water that's flowing equatorward in the Benguela current, and then there's warm tropical water flowing poleward, called the Angola current, and the general kind of gyre flow. And they meet, and there's an ocean front. If you look then at the wind stress, this is this tau y variable I mentioned earlier, meridional wind stress. It has this maximum, and the maximum meets coast at 2 points. So this is why we call it a double core atmosphere jet. Further south in Namibia, Luderitz upwelling, and on the border between Angola and Namibia's Kunene, Cape Frio upwelling, where strong winds occur. These are the maximum of the wind stress. And if you look at the sea surface temperature, you can see the cold water. This is the upwelled water along the coast associated with the Benguela current and the upwelling. And the front is here between cold water to the south and this warmer water further north, the Angola-Benguela front. It moves north and south. It's not always fixed like this bar kind of shows, but it's always there with some variability. And it's hard to simulate the position of the front. Off Northwest Africa, it's maybe even more complex environment, but kind of curiously, I think that the models do a bit better here. It's kind of interesting question, why? The image on the left is a sea surface temperature image from satellite, and you can see cold water off the coast of Northwest Africa. And then on the right here, I'm showing the annual mean wind stress, this tau y. And it's got 3 maxima. This is from satellite of a cape here, Cape Gear. Another one in the lee of Canary Islands, so there's a kind of an island effect, but it's getting close to the African coast. And then another maximum of Cape Blanc. So there tends to be this fact that maxima occur slightly downstream of capes. I think there's been a technical term in the literature, talks about an expansion fan downstream of capes, and there's also wind stress curl associated with it. So these are key points for the upwelling, and you can probably see it in the SST image as well, the influence of these regions. Okay, and this is the final slide from the introduction. People want to know what's going to happen under climate change. So the hypothesis that was raised by Bacon in 1990 was that there would be an intensification of coastal ocean upwelling due to stronger winds along shore. And the idea here was that under a warming planet, the land would be warming more, there'd be an increased land-sea contrast, because the land would be warming more than the ocean. The pressure gradients would strengthen, and the alongshore flow, shown as these arrows, would strengthen. So that's what's shown as you go from this schematic. This is from back on 2015 schematic, shown at the bottom. As you go from present day to future, these wind vectors strengthen. This is representing a relative thermal low over the continent. It gets stronger due to the warmer temperatures under climate change. So you have stronger winds. And this also includes another related hypothesis, which is raised later by Rikachewski et al., 2015, that there might be a poleward movement of the upwelling associated with poleward shift of the Hadley cell, and the subtropical high is just kind of planetary circulation changing. And then because the subtropical cell is moved poleward, so the upwelling winds. So these are two related hypotheses. So I should move on and now cover the coupled climate models. Work started, Peter Jen described some of these results from earlier version of it was called CCSM4 then. Then we've had a series of papers led by myself and Jason Kurian and Ping Chang, which have looked at high and low resolution versions of the community Earth system model. Again, with some similarities to the community, like CMIP5, CMIP6 results. A word or two about community Earth system model. Not everyone's familiar with this. Version 1 of CSM was described in a paper by Jim Hurrell, 2013. The atmosphere model is CAM5, the land model is CLM4, ocean model is POP2. If you want more information, please go to the reference. And the high resolution we use here is a 1/4 degree in the atmosphere and land, and a 1/10 degree in the ocean and sea ice. So it's a global model. And then the low resolution is 1 degree in both atmosphere and ocean. And that's described in these papers led by myself in 2014. And then Ping Chang and a group of us made much more extensive set of simulations. In the first paper, we had 100-year simulation. Now we have essentially, people familiar with CMIP, we have the equivalent to the deck with a long PI control and transient and climate change runs and ensembles. So this is quite expensive, but we've done it. And some of the runs are described in Chang et al. 2020, but we've had more runs since then. I'll show some results from CSM2 that just from standard resolution paper, and the chair at the time was Gökhan Danabesoglu, and that used CAM6, CLM5, and POP2 again, and I just chose standard resolution of 1 degree each, atmosphere and ocean. I'm just highlighting the key components for what I'm looking at. And the final word is that CSM version 3 is under development. Dave Lawrence is the CSM chair currently. And one of the main changes that's going on is the ocean model's been replaced by MOM6. But that's still under development. And if you look at how these coastal winds and change with atmosphere resolution, it gives a first idea of the kind of results I'm going to show later. This is from the previous version of CSM, called CSM4, with a 2 degree atmosphere model. And what you can see, you have these wind jets, and what I've shown here is the absolute value of the wind stress. So positive means a maximum of strength. You have these wind jets, but they're located offshore and along the coast. I don't know if you can see that. They weaken quite substantially. You can see it off Peru, Chile, and you can see it off the Benguela. There's a strong weakening. Not quite so clear in the northern hemispheres. And then as you move to a higher resolution of half degree, these features, these maxima in the wind jets, get closer to the coast. It's harder to see the weakening. It is there, but it's over a very narrow region. So that's half degree CCSM4. And the bottom is the satellite data from QuickScat, and hopefully you can see that the QuickScat is a bit closer to the half degree model. And if you focus on the Benguela, it's quite marked. This is the 2 degree result. You see the wind maxima offshore. So this is the land mass here. And weak winds towards the coast. This gives rise to a poor representation of upwelling and coastal currents. As you go to 1 degree, it gets better, gets closer to the coast, still a bit far offshore. Half degree, it's getting better again. Quarter degree, the wind jets are very close to the shore now, which is good. There's still a strong drop-off if you zoomed in very close, and you can't really see it here. And these are the observations where the maxima is really almost at the coast. The drop-off goes over a very small region. So this is from the paper by Ping Chang et al. If you look now at the response of SST to these winds in the Benguela, I'm going to compare the high-resolution CSM. This had quarter degree atmosphere, 10th degree ocean. Low-resolution CSM is 1 degree in both fields. And what hopefully you can see is that with the low resolution, you get 1 maximum of the wind jet. With the high resolution, you get these 2 maxima. This is a double core jet. And that's more like the satellite observations. The observed SST has a cool SST along the coast. With the high resolution, you see this cool SST in the southern part of this Benguela system, but it's too warm at the north. This is kind of a typical problem. And this is to do with what I mentioned earlier, very hard to simulate the front between the cold and warm waters, which is in these latitudes. The low resolution has even kind of weaker upwelling and hardly represents the upwelling at all towards the south. And if you look at the summary, this is the high resolution SST minus observed SST, and look globally. It's good in most of the eastern boundary upwelling systems. In the Benguela, we still have this warm difference, which is arising from this difficulty of representing the front and not enough upwelling at the higher latitudes. But in the southern system, it's much better than other resolutions. And if you look at Northwest Africa, again, you have this triple core jet. This is the observations, 1, 2, 3 cores, hopefully just about visible. The high resolution model is capturing, I'd say, most of that. 3 cores, it may be merging the bottom 2. And the low resolution atmosphere model basically just has one core. And the SST response, this is the observations. You see the cool water due to the upwelling. This is the high resolution, looks very good, representing this cool water. The low resolution is missing the cool water along the coast. And this is an example. If you compare this with CMIP, maybe CMIP is a bit better than this low resolution model, but it's kind of qualitatively similar. And moving to CSM2, things didn't get better for this particular issue of how well the SST is represented compared to observations. So this is CSM2 SST minus observations. So you have it's kind of warm in the whole tropical Atlantic, and it's highlighted in the Benguela region. This was CSM1. It was a little bit better, not such a warm bias. And I'll point out, well, one thing, CSM2 was globally warmer, so that part of why it looks warmer in the South Atlantic. And secondly, there are teleconnections which occur between the tropical Atlantic and the coastal upwelling. That's another part of the story I'm not going to focus on, but that's another challenging thing. So you have problems in representing the equatorial Atlantic, the winds, and the coupling to the ocean temperature. I'm going to quickly go through the regional climate models. Here we're going to be using WRF and ROMS. They'll be uncoupled from papers I'll describe in a minute. And so regional models that people in this location know, they can be used for downscaling, and they may also be used for upscaling in some coupled contexts. But they also allow for focused process study, where obviously you can fix the boundaries. And that issue I showed on the previous slide, where the tropical Atlantic was really connected to the Benguela and causing problems, you can kind of isolate that and maybe remove that. So you can look at the local processes. So that's the kind of thing we're doing here. So we're using WRF, developed here, Skamrock et al. 2008. This work is in a paper by Patricola and Chang in climate dynamics. They used a range of different resolutions, and going from 3 and 9 kilometers all the way up to 81 and 243 kilometers. I would say these are not really the kind of resolutions that WRF is probably used for. It's a regional model known, and people want to use it for higher resolution. But I think it's illustrative to actually run it at these coarse resolutions. And ROMS, the Regional Ocean Modeling System, and has been commonly used in the ocean community. And the resolutions used here, this is by Jason Kurian and a group of us, range from 3, again, to 81 kilometers. And again, 81 kilometers is coarser than you'd normally use ROMS for, but it's still illustrative. And that was published in Climate Dynamics. I'll make a point that we do have a coupled system of WRF, ROMS, and CLM coupled in the CSM framework. Is published a paper by Dan Fu et al. In BAMS, but we haven't done a precise upwelling experiment with that yet. And there's also a focus in the oceanography section and CGD now on using regional MOM6, because MOM6 is a new global model. And I'm going to show this in figures. This is what we call the coastal low-level jet in WRF off the Benguela. And if I showed maybe these panels on the right will illustrate why we call it coastal and low-level. These are sections, I think it's at 21 south, so going through the Benguela. The landmass here is as a function of longitude and pressure. And you see that the jet is a maximum very close to the land, quite low level. I think this is something like 9.75 hectopascal. This is from CPSR. You can see it also in JRA 55. So this is the low-level jet, and then these are showing the spatial distribution of that jet. And similar to what we found with CSM, this is satellite observations on the left, double core. As you go from, these are the high-resolution runs at the top. They have the double core, 9 kilometers, 27 kilometers. I'm not showing the 3 kilometer here. And then as you go coarser, it goes towards a single core further offshore, which is like this CMIP5 representation. So these plots are of tau y. And so it actually is quite good that you see some consistency with CSM, which uses CAM. Both these models show similar behavior. There's differences in the detail if you really go into it, but broadly similar behavior in their sensitivity to resolution. And then how does the SST respond in ROMS? This is maybe a complex plot, but if I'm going to tell you that finer ocean resolution is as you go to the right. So you start with 81 kilometers here on the left, and you go to 3 kilometers. And then finer atmosphere resolution as you go to the bottom. And you start, so the top row is all with 2-degree winds from the core data set. Some people know about this. And the bottom row is all with 27-kilometer winds. Now, what's notable immediately from this, and what I'm showing is the bias of SST relative to observations. What you see is all these cases with 2-degree winds actually originate from NCAR reanalysis. They all have a large bias or error along the Benguela. There's not much sensitivity to ocean resolution. And the reason here is if the winds are not good enough quality, if the jet is too far offshore, it doesn't matter what ocean resolution you have, you will not get a good response. It's just the winds are not good enough. If you move to WRF at 27 kilometers, which is one of the good high-resolution WRFs, you see that the SST error is much less. There's a kind of smaller sensitivity to ocean resolution, which is as you go to the right along the panels. But the main take-home point is atmosphere resolution is key, and you need fine atmosphere resolution to resolve the atmosphere jet. And once you've done that, then you need the ocean resolution to resolve things like the upwelling front and the eddies. But in terms of SST, the biggest bang for your buck is the atmosphere resolution. Okay, I should quickly talk about historical upwelling. So these were from, particularly item 2 was from free-running coupled models. Couldn't really compare variability with observations. So I'm going to look at forced ocean sea ice simulations. Steve Yeager led a lot of this work, and we're trying to get this published in this paper going through Journal of Climate. And I'll also discuss a kind of even more exciting aspect of a biogeochemistry and a fish model, which have been combined with the ocean sea ice model. So a bit more detail. The ocean sea ice model is forced by a JRA 55 product, which was developed by Hiroaki Tsujino for forcing an ocean model. I'm not sure, I will compare some examples with core, which had 2-degree winds. The ocean resolutions I'll be showing are 0.1 degree or 1 degree, similar to the ocean resolution from the couple model. And there's been some work published in these papers here. So that's the ocean and sea ice, but it's now being coupled to a biogeochemistry marine model, which is the Marine Biogeochemistry Library, MARBLE, collaboration with CGD and outside collaborators. And then the fish model is an offline global fish model, so you apply it to the results already produced. Originated by Petrick et al. 2019. Kristin Krumhart and collaborators have been applying it now in the POP model and MARBLE model. So I'll start first this one slide on just the physical variables. This is SST, looking at variability. So this is the monthly non-seasonal variability. This is Northwest Africa. The anomaly from the climatology, this is anomaly in degree C, time period from 1993 to 2018. And the black line here is observations, and there's 4 different models which I described in the previous slide, different ocean resolution, different forcing. The key point for this is they all do really well. And these are correlations of model of observations, and they're 0.9 or upper 0.8. So a very good representation of variability of Northwest Africa. This is the Angola-Benguela front north of the Benguela. It's not quite so good representation. And this is the kind of main Benguela system. Again, it's more of a mismatch between models and observations than in the Northwest Africa system. And the correlations are more like 0.5 to 0.7 for this region. And that may relate to the biases that I showed earlier in the mean state. This is the system schematic for the biogeochemistry model, which is on the left. This is the main marine biogeochemistry model for CSM. So that's coupled online to the ocean and sea ice models. And then on the right is the fish model. It's called Feisty, which is, an offline model to look at different size classes of fish, which you can probably anticipate is a very hard aim, and I'll kind of talk about that in a couple of slides. This just starting with I'm showing the chlorophyll here. This is from satellite data and analysis from satellite data. This is from CSM, high resolution. Qualitatively, very similar. If you look at the boundary systems, it's maybe a little bit weaker in high-res CSM than satellite observations, but we need to look more carefully, and that's of Northwest Africa. And these are some, not quite snapshots, but monthly means, just show an idea of the spatial variability. This is of Northwest Africa, March 1979. From the high-res model, you have all the eddying and filament variability. Low-res model has none of that. It's just a 1 degree, does not resolve eddies. And similar off, this should read Benguela, similar off to Benguela. Strong eddying activity in the high-resolution model includes the Agulhas rings, which are generated to the south. But they don't heavily interact with the Benguela further north, I think. Maybe they interact with the southern Benguela. But anyway, a lot of eddy variability not represented in the low resolution, which actually seems to have too broad and too strong productivity. And then you can look at time series of fish catch yield. So this is what I say is a very difficult target. You can imagine in the real world, fish catch depends on a lot of things, including human factors and the amount of fishing, the trawling fleets, and so on. So this is a difficult target. I start with showing an example from the California current, this being, I think, well observed for the fish catch. And the solid line is the model, and the dash is an estimate of the real fish catch. And you see the variability is quite well captured here. The correlation is quite high, 0.64. If you look at we have different axes, however, for the model and observed fish catch, and the model is too strong. But say this is this difficulty of trying to estimate this hard quantity. But the variability is well captured. For the Benguela current, it's kind of the variability is not well captured, and the amount is also off, but maybe less so than in California. The absolute amount may be more like half, a factor of 2 difference. Here is a factor of 5 or something. But these are brand new results. In fact, I received this result yesterday. And these are, I think, novel in a global context, a 10th degree. And these are challenging things to estimate from the real world and from the model. So I'm going to finish now, try and wrap up with upwelling under climate change, where we're using high and low resolution CSM. And just to recap, I talked about the hypotheses for an enhancement of land-sea contrast, the Bakken hypotheses, poleward expansion of Hadley cells and the subtropical cells and upwelling. And then this kind of newer idea of that the geostrophic flow is important. And this is a result on the geostrophic flow by Ding and Alexander et al., 2022. And what is shown here is the trend, or it's actually an epoch difference from future minus current, or historical. And this, I believe, is a function of latitude and calendar month. This is the total vertical transport in this panel. Top right, this is the wind stress induced part. This is the Ekman part, qualitatively similar. But then bottom left, this is the geostrophic part. And you see that it's similar magnitude, so it has a major influence. And then when you combine them, you get something which is indeed like the total vertical transport. So this can be measured from the model directly, and then this is the 2 parts estimated. And there's a paper by Zhao Jing et al. mention that this also happens in high-resolution CSM. And I want to summarize results from a paper by Ping Chang and my collaborators and myself, so Texas A&M and CDD. What we found is that for the upwelling, it's not as straightforward as the back-end hypothesis. Has a number of different factors. Horizontal processes are important, not just vertical, particularly for SST. The wind stress curl is important, that was mentioned earlier. There's a very strong sensitivity to the domain considered. Are you going to be looking at the southern part of the upwelling system or the northern part? And there's no universal process. For example, if Northwest Africa, instead of stronger coastal winds, you get weaker coastal winds, you get changes to wind stress curl, but you get stronger upwelling. So that's counterintuitive, and maybe that's related to the geostrophic part. And you get cooler SST at the coast. Off Benguela, there's generally stronger winds and wind stress curl, and there is increased upwelling, particularly in the southern part, but the SST increases, doesn't decrease with more upwelling due to horizontal advection. So the SST along the coast is actually warmer than offshore. And it's probably time to wrap up. This is the summary. The global climate model representation of EBUs, the upwelling systems, is improving. And I'll compare it to, say, approximately 2 decades ago, maybe running 2-degree atmosphere models. So there's been a big improvement since then. The atmosphere resolution is key to represent the coastal low-level jet. But the fine ocean resolution is needed to show upwelling front eddies and jets. Regional models offer promise to downscale, and there have been some projects where you also upscale to the global model. As I say, the typical approach is to downscale an ocean model. This has been done in several papers in the community. But ideally, the atmosphere model should also be refined to improve the wind forcing. So if you use atmosphere model from a coarse global model, 1 degree and so on, it may have these problems with the atmosphere jet. So even if you refine the ocean resolution, you still have problems. The historical monthly non-seasonal variability is fairly well represented in forced ocean simulations. And I didn't talk about this much, but variability of physical fields such as SST, a lot of it's driven by large-scale climate, not just local wind forcing. You can think of ENSO, for example, affects the California current system and so on. And then we're getting promising results when coupled to a BGC and fish model. It's not perfect results, but these are novel simulations. And finally, the climate change of upwelling is affected by a number of different factors, not just one. Land-sea contrast, poleward expansion of the atmospheric circulation, the Hadley cell, wind stress curl, and then the geostrophic offshore transport effect. So that it's more complex than originally thought of. So I'm going to wrap up there, and thank you again.
Thank you so much, Justin. I don't see any question in Slido right now. I don't know if, just questions in the room.
Yeah, I guess two questions. One's, is it too simple to say that more upwelling means better fish catch, or is that a good generalization of, is it correlated?
I think that's too simple, and I'm not the expert, but I've read papers where a more increase in vertical upward velocity does not exactly equal more higher fish catch. There's all these steps in between, and the nutrients and where populations are, and the depth in the water column and so on.
Because there was a interannual variability or seasonal and correlated. And it seems like a model is capturing something that the upwelling or the atmosphere does. Is it correlated with, it's not correlated then with upwelling, it's more correlated with something else that...
I think it's complex. And taking the example of SST, the large-scale factors are important there, which drive changes in the wind, and they also drive ocean teleconnections, coastal waves. For the BGC and the fish, I think large-scale process is also important, but it's just more complex than the simple stronger vertical velocity equals more fish. But the vertical velocity is an important factor in the whole thing.
And I had a second question. I don't know, I have it on the screen, but a second question, which was you were showing one-way ocean coupling, I guess, to the atmosphere, and do you think there would be any benefit from a two-way coupled model?
What we've worked at in CGD in the ocean section had a couple of projects where we fed the regional ocean model back to the global ocean model and coupled it to the atmosphere. It's not, as far as I'm aware, an offshore flat's been done for the atmosphere yet, and there could be benefits. There could be upscaling benefits of if you improve the resolution in a small region will affect globally. But definitely the kind of online downscaling aspect would be important. And we haven't quite got there yet, and maybe other groups have done this, but we had have a regional couple model of WRF and ROMS and CLM. At the moment, it's mainly used with reanalysis boundary conditions. I think some people have applied CSM boundary conditions, but not online. I think they've done it offline. There's definitely a big benefit of at least doing downscale online of high resolution regional with the global model. The other alternatives people are exploring are the mesh refine type of I think MPAS can do it, and CAM-SE. So yeah, that's other things being explored.
I have a question. So it seems pretty clear from the higher resolution runs are doing quite a bit better, right, in almost all of your cases.
Yeah.
So what's limiting in making progress there? Is it computational stuff? Is it the boundary condition, the observations that drive the model? You mentioned expensive runs and so forth. When you do these coupled models, do you really run into computational limits?
Yeah, the high resolution is very expensive to run. I'm trying to remember when I was involved in the running of it. It was something like 200,000 core hours per simulated year. And that was on an older system, Yellowstone. So that's definitely a challenge, and that's where these kind of downscaling to some regional things maybe a bit more attractive. I think it's mainly the computational expense is the challenge. This is a community, and CSM is a community model, and people in universities don't always have access to high computing power. So there's always a balance, and that's a challenge. Although the university community can apply for computer time at NSF NCAR, so that's not a complete barrier. But they are very expensive to run the hybrid and high resolution, and the atmosphere actually is the most expensive. So, for example, when you go use CAM and go to quarter degree, that's the most expensive part. The ocean at 1/10 degree is not so expensive.
So the coupling doesn't add a lot of expense.
No, it's not the coupling. It's the components and yeah.
Because in there, that CSM, is it CESM 2? You showed one result where the anomalies were actually quite high, even in the middle of the ocean, like even up to 5 degrees of temperature anomaly.
Yeah, so there's tuning processes that go into global climate models, and I'm not getting it visible on the screen. I'm trying to bring up the map. And yeah, resolution doesn't always cure everything. There's the physics and the tuning are also, also very important. I don't want to brush those away, and they might have a more global scale effect, and that's obviously what a lot of the model development is on the physics side as well. But I would say for this particular process of coastal winds causing upwelling, resolution is very important. And I'd say that the atmosphere resolution is the main thing. And then you can go into details, and I think actually WRF might be a bit better than CAM at the same resolution. But this is when you go into details. In general, it's just the resolution of the atmosphere is key. The physics will then modify things. For example, as I showed earlier on, the stratocumulus low clouds, and they're also hard to represent. And they will affect the surface energy budget and the SST. So that's another factor, particularly globally. They cover a larger area.
Yeah, thank you.
I think that we wrap up here. Thank you so much. This was really interesting. Yeah, so thank you so much.
Anna. Yeah, and thank you for coming.
Yeah, thanks.
Thanks.